Time to move on to yet another metamorphic reaction, and we'll increase the number of chemical components. And so this is a question of what happens to a mud when it's buried and heated. This is a typical metamorphic process, and a typical set of minerals that you would find in a mud that eventually became a rock are the collection of phases: muscovite, quartz, potassium feldspar, an aluminosilicate like andalusite, and water. Now, of course, if it's andalusite, it could be sillimanite if the temperature and pressures are higher, or it could be kyanite if the pressures are higher. So let's analyze this system just as we have the previous two systems. First of all, muscovite has a chemical formula that looks like this. It has potassium, it has aluminum, it has sheets of silica, and it has bound water. Now the quartz is, of course, simply SiO2. The feldspar, the potassium feldspar, has potassium, aluminum, and silicon. The andalusite, sillimanite, and kyanite have aluminum and silica. And the water, of course, is H2O. So we have all those phases. How many chemical components are there? Well, we count them up again. We have potassium, aluminum, silicon, and hydrogen. There's 4 components. So we probably are looking for 4 building blocks made of those cations. And we're free to choose how to make those building blocks as long as they go together to make our collection of minerals. And I'm going to choose ones that are based on a single cation in each of the building blocks. So 4 components based on potassium, aluminum, silicon, and hydrogen. Let's make the hydrogen building block HO1/2. You see, we're not confined to making a standard chemical formula with integer number of oxygens. I've just made one where there's 1 hydrogen and enough oxygen to balance the charge, and hypothetically it takes half an oxygen to balance the +1 of the hydrogen. The silicon, SiO2, I'll just use the standard quartz building block. For the aluminum, let's divide alumina through by 2, so we have 1 aluminum and 2/3 of an oxygen. And finally, here's an interesting choice. Let's use potassium in the feldspar structure. So I have KAlSi3O8. So that's a perfectly reasonable set of building blocks. 4 of them, they encompass the cations in our system. And in fact, you can show that adding together integer numbers of these building blocks will give you all of the chemical phases, all the crystal and water phase that's represented on the left. Okay, we know there are 4 building blocks. We can substitute into the phase rule. And that's going to tell us that in divariant areas, we have a maximum of 4 phases. We can have 5 phases along univariant lines, and we can have up to 6 phases at invariant points. Okay, let's move on to trying to represent this information, and we have a problem now. How do you plot 4 chemical species plus pressure and temperature? As noted at the beginning of this video, we've run out of axes in a 3-dimensional world. Well, we're going to have to do something clever. And remember that we used a triangle plot to represent 3 phases. We have 4 now, so what do we do? Well, how about trying, instead of a triangle, let's try a tetrahedron. A tetrahedron is made up of 4 corners with triangular faces. So let's put the 4 building blocks in a tetrahedral pattern. There's the water component, the silica component, the potassium feldspar component, and the aluminum component. I can draw triangle drawings between any 3 of these. For instance, here's a triangle, a ternary diagram between water, silica, and feldspar. I could also draw a ternary diagram between water, silica, and aluminum, or silicon, feldspar, and aluminum. Put it all together, and I have a tetrahedron. Now let's plot our phases on this tetrahedron. Water's simple. It's down at the vertice on the left side. Silica, quartz is easy. It's at the lower vertice there. Potassium feldspar plots on the other corner. Now, the aluminosilicates contain no potassium and no water. They plot along the edge between silica and alumina, as I've shown there. Muscovite, that's a problem child. Let's see, it's made up of 2 units of water, it's made up of 2 units of the alumina, and it's made up of 1 unit of the potassium feldspar. It doesn't have any units of the pure silica in it. Thus, it plots on the back face of this tetrahedron. And I show it, it's behind the front, it's on the back surface, and there it is. Okay, all the phases are plotted, but we have this 3-dimensional figure that's a little bit hard to work with. So we need to make yet one more approximation in all of this. And I'm going to do that by taking a line starting at the location of water, coming up through the compositional point for the muscovite, and extending on to the edge of our triangle diagram. I'm going to plot that there as a white dot. It's a white dot because it represents the projection of muscovite onto a ternary diagram between silica, potassium, and aluminum. Now, why do we do this? Why can we get away with this? Well, the assumption is that water is always present on Earth. Whenever we have a metamorphic reaction, water is around to get sucked up to be incorporated into the crystal structures. We don't explicitly need to plot water. We can get away with letting water be implicit in our representation. If we do that, we've reduced the number of components from 4 to 3. That will reduce our number of phases by the phase rule by 1 as well. And we can simply use the ternary plot outlined in yellow. And that's what I'll do in the next page. So here's our ternary plot with aluminum at the top, silica on the lower left, and potassium feldspar on the lower right. Kyanite, andalusite, sillimanite plot as shown there. The projection of the muscovite plots as shown there, and I've made it a hollow dot simply to emphasize that it's implicit that there's water behind this projection. Quartz is the lower left and K-spar is the lower right. At this point, I want to clean it up a bit, replace all that was in the lower left corner with Q, Q standing for quartz. You know that's SiO2. I replace the lower right with KFS, the simplest, shortest abbreviation for a potassium feldspar. Replace muscovite with M and remove the alumina from the top. It's implicit. So we have a ternary diagram with aluminum, quartz, and potassium with the phases plotting as shown here. Next, let's draw some lines. These lines connecting phases are what we call tie lines. And the way to understand a tie line is that a tie line connects mineral phases that are in equilibrium with each other. So this diagram here tells you at a glance that equilibrium exists between quartz, muscovite, and an aluminosilicate. In contrast, if I change the tie line to this direction, that implies that we have muscovite, an aluminosilicate, and potassium feldspar in equilibrium. So in summary, we've taken 4 compositional dimensions and we've figured out a way to represent it on a 2-dimensional plot. On this 2-dimensional plot, we have a way with tie lines and a ternary triangle, a way of seeing what's going on, what phases are in equilibrium with what phases, and this will apply to a particular pressure temperature point.